In this video, I'm going to be talking about the internal resistance of a cell, or a battery. Please read the success criteria of what I plan to cover in this video. Okay, so I've used the Fet Simulation here. You can use the little symbol in the bottom to access the page. And what I did right here is I'm looking at the potential difference in a cell, and if you notice right here, I have the circuit open, which means there's no current flowing. And in that case, it tells me that the potential difference across the battery or the cell is giving me 9 volts. But as soon as I close the circuit here, you can see that the potential difference now, or the voltage, has dropped to 6.43 volts. And what we need to talk about in this video is why that happens. Now, batteries or cells, they're not perfect, which means when the electrons move through, and that's what these blue dots are trying to symbolize, it actually takes some energy to move the electrons through the cell itself from one side to the other. That means as soon as I have current flowing, some of the energy per charge, or the potential difference, is going to be used up inside the cell itself. So what does this tell us? Well, it means that there's going to be a difference between the total amount of energy that I can provide to the circuit per charge compared to what the terminal difference is. And the terminal potential difference would be from one side to the other. As soon as the current starts to flow, not all of my energy will actually be able to be used in the external circuit. Now you can see here that I have a battery resistance. That's the internal resistance I'm talking about. It's set at 4 ohms. We'll come back to that later. And I have here a 9-volt battery. So how would I be able to calculate that 4 ohms, that internal resistance? Well, let's model a cell, pretending here's my cell or my battery. And let's say it has 2 parts to it. One part would be the source and another part being an internal resistor. Notice I have everything here already in one series circuit. Our terminal potential difference would be from one side to the other. And as I said before, when there's no current flowing, it would actually be measuring, if I had my voltmeter here, when there's no current flowing, I'd actually measure my EMF. When there's a current flowing, then it's going to drop and my terminal voltage will now be less than the EMF. So what I've got here is I've got Kirchhoff's law. The total potential increase would be the EMF equals the total potential decrease. This is my terminal voltage and the potential difference that was lost due to my internal resistance. And using Ohm's law, V equals IR, that will be the current. Everything's in series, so the current is always the same, times little r being the internal resistance. If I group these things together, I have my EMF equals the current bracket times the resistance I have outside my circuit, that would be right here, plus little r, which will be for my internal resistance. So here's a better diagram of how I could actually set up a circuit to measure this internal resistance. You see I have a voltmeter that's going to measure my terminal voltage here, and I have an ammeter that's going to measure the current. Again, everything's in series, so everything will have the same amount of current flowing through it. So what will I do? I'm going to take this variable resistor, and I'm going to vary the resistance through it. So I'm going to vary R. And as soon as I do that, it's going to change the total amount of resistance of my circuit, which means it'll change the current flowing through it. And because I have here the potential difference loss due to the internal resistance, it'll be the current times little r. It will vary the value I'm going to have as a terminal voltage. I'm going to do this for 5 different resistances, and then I'm going to take my values and plot them on a graph. So let's think about this. We had that equation E equals I R plus R. If I expand that, this is our potential difference across the terminal voltage, plus I R. Now if I rearrange that and move it around, I'm going to get this potential difference, the terminal voltage, equals negative the internal resistance times the current I'm measuring, and our EMF. if I graph this with a V here and I here, now let's notice that's on my Y, that's on my X. That means that this value right here will be my gradient, and this value right here will be my y-intercept. Let me just do that one more time in case you didn't see it. This is our equation of a straight line, y equals mx plus c. So this is on my y-axis, this is on my x-axis. So whatever value I have added here, in this case is my EMF, that will be my y-intercept. And whatever I have in front of my I, in this case negative r, that will be my gradient. So I went to the Fet simulation and I did exactly that. I changed the resistance of this resistor here. You can see I have different colors. The different colored bands stand for different resistors, and I measured both the voltage and the current. And when I graph it, here's what I get. I have my potential difference on the y and the current on the x, and I got a straight line with a negative gradient. Now, the negative gradient is important because in our equation it says our gradient equals negative r. So in this case, my gradient is negative 3.998. That means r is going to be about 4. And if you remember that, I said earlier I had it set at 4 ohms. The other thing is my y-intercept right here. If I take a look on my chart, it says that it was 8.995, and we had set that at 9 volts, so that all works out. So let's go through an example of how we can use this. First part, we've got a battery with an EMF of 9 volts, an internal resistance of R. So once the current's flowing, I'm going to have less than 9 actually going to be able to be used in my circuit. And the current is, we're told, is going to be 1 amp. Now, in this case, part A, calculate the potential difference between A and B in the circuit. Okay, so let's start by realizing that we've got 2 ohm resistor and a 2 ohm resistor here, and they are in parallel. So that tells me 2 things. First of all, it's going to tell me that they're going to have the same potential difference. That's because the 2 things in parallel are going to have the same amount of potential difference. The other thing it tells me is that the current is going to be divided equally. So that between A and B, we know that the current is going to be 1/2 of the 1 amp, which will be 0.5 amps. Now, if I use Ohm's law, V equals IR, we're going to get 2 times 0.5, and we're going to get 1 volt. Part B, calculate the internal resistance. Now for this, let's use Kirchhoff's law. It says the total potential difference around a loop equals 0. Or another way to say that is the total potential increase will equal the total potential decrease. So in this case, I start off with having a potential increase of just our EMF. And I've got different places where that's going to be used. First of all, it's going to be used inside the battery, the current times the internal resistance. I'm also going to have it used at my 6 ohm resistor, so that would be 6 times the current, which is going to be 1. And then it'll be used at my 2 ohm resistor as well. So let's substitute in some values that we know. We know the EMF is 9. I know the current is 1. I don't know R. This is going to be 6 times 1 and 2 times 0.5, because remember, only half current goes through that resistor. That tells me my internal resistance is going to be 2 ohms. Finally, it says state and explain one reason why it's an advantage for a rechargeable battery to have a low internal resistance. Let's look back here to our equation. As soon as we do this, as soon as we have an increase in our internal resistance, that means there's going to be a less potential difference available to the circuit. Another thing we can think of is as soon as we have a higher internal resistance, what that does is it's going to reduce the current that's flowing through our circuit. So if we need our current to be able to produce something such as heat in our circuit, then having a lower current will be affected. And finally, we could also say that the energy that could be used in the circuit is now wasted. So if I have this much amount of energy per charge that I could use in my circuit, the more internal resistance means I have more of that energy used in my cell and less in my actual circuit. So I had 3 different options. And there's a summary of what I just said. Let's look at another example. We have a car battery with the EMF of 12 volts and an internal resistance of 5 times 10 to the minus 3 ohms. And the battery is used to provide a starting motor of a car with a current of 800 amps, which is a very large current. Part 1 says calculate the potential difference across the terminals of the battery. Alright, so let's start with our equation. I'm going to expand that out. We can also think about there's our terminal voltage plus the current and our internal resistance. Moving this around and substituting our values, that's going to be 12 minus 4 gives me 8 volts. Okay, part B. Calculate the rate of dissipation of energy due to its internal resistance, stating an appropriate unit. Alright, so let's think a little deeper here. The rate of energy. Oh, that means it's looking for power. So what we're looking at is the power that's going to be dissipated due to the internal resistance. So the one I usually remember is P equals IV. But I don't have the potential difference right now, or I could use this value. What if there was a mistake? What also I can do is I can say P equals I squared times resistance, just in case my part A had a mistake. Let me put in the values here. This is going to give me 3,200, and don't forget the question says stating an appropriate unit. As soon as I knew it was power, I have to have the units of watts. And with the IB, what happens is, since it's told me to state an appropriate unit, even if this value is incorrect, if I have watts here, I'm going to get 1 mark. And finally, part C, state and explain the effect of attempting to use a battery with a much higher internal resistance. Now, as a side note, I want to just point out that we tend to use lead-acid batteries to start our cars. One of the reasons why is they can supply that really high current that we're talking about in this question, but they do tend to have higher resistance, and that's why we wouldn't use a lead-acid battery with its low energy density for something like my phone or a flashlight. So if I increase the internal resistance, as I said before, that would reduce the amount of total current available. So what's the issue with that? Well, maybe the car won't start. So please read the success criteria one more time to see whether or not this video has helped you say yes to the success criteria.